Now, we need to, talking about gravity and the orbits of planets, we would be remiss if we didn't talk about Kepler. And Kepler came up with these laws of orbital motion, or orbital mechanics. But the thing is, he was before Newton, and so just like Newton was very clear that he doesn't know why gravity works, he just knows the form of the equation of gravity. Now, so you got to keep this in mind with science. Newton does not know why. He knows what? How. Newton knows how. Now, Kepler knows even less of the how, but he still knows some how, but just not quite as much how. Let me show you what I mean. Kepler, based on very good astronomical studies, was able to determine some very some universal laws of motion of the orbits of planets. For example, if here is the sun, he showed it was known from observation, telescope observation. Well, not. It was known from observation that the orbits of planets were actually ellipses, not circles. They were ellipses. Now the thing is, yes.
What is it?
Oh, good question. An ellipse is an oval, and mathematically, the ellipse has 2 points of focus known as foci. In this case, one of the foci is the sun. The other one is this imaginary point. So this will be F1 and F2. And there's a mathematical relationship between F1 and F2, which is this. And you can show this very easily with a piece of string and 2 nails. Great activity to do with kids if you're teaching kids. If you measure the distance from let's pick a point along the oval, or along the ellipse, to use the fancy word. If you pick a point anywhere on that ellipse, and you draw a line from there to there, and we'll call this L1, and we'll call this L2. No matter where you do this, anywhere on this ellipse, let's do it at a different point over here. The ratio, or the sum, rather, the sum of L1 plus L2 is going to always equal some number n. That's the same for every point along the ellipse.
So it's constant.
It's a constant. But bear in mind, L1 and L2 are changing lengths,
Right.
but if you add them up, it's always the same. That's what makes an ellipse an ellipse. So the orbits of planets are ellipses, and there's some other interesting stuff that happened, and this is where Kepler comes in. Picture this. Now remember, you're falling. The planets are falling around the sun. And if you imagine yourself falling around the sun in some giant galactic carnival ride, so let's picture it this way. I'd love to do some kind of 3D animation of this because it would help us picture it, but maybe I can describe it well enough. Let's say you're at the very, let's look at the whole ride from the side to begin with. Here's the sun. And you start your ride by getting pulled up to some very high point. Let's make this a little more of an elliptical ride. Okay? And then you get pushed right from this point right here. Now, you start falling. You're not going very fast at the very top. You're just given a shove. But then you start falling and you're going faster and faster and faster down. And then you whip around the sun at super high speed, and then what happens is you go up away from the sun. you start to slow down to your slowest point. So your slowest point is up here, and your fastest point is down here, right? Does that make sense? Yes.
So it would be almost like straight on a street.
Yeah, it's related to that, definitely, yes.
And that's with each planet's orbit, right?
Every planet is falling around the sun, and the moon is falling around us and the sun. Yes.
At what point in this year is the slowest and the fastest?
Okay, we'll get to that. Now we'll draw the orbit from the top again, but I'm just drawing it that way so that we have some understanding of what's really happening, because the planets are really falling around the sun. So now let's look at it from the top. So here's the sun. Here's the elliptical orbit of any one of the planets. And in reality, they're almost circles. They're very, very shallow ellipses. I'm exaggerating this so that you can see it. But things like comets, comets have extremely, very elongated ellipses. Yeah. Yeah, exactly. Comets are very, very stretched out. But now let's look at this. So here's the fastest part of the year of this planet. Here's the slowest part of the year. Watch this. This is one of the rules that Kepler came up with. Let's say it takes 30 days. 30 days for the planet to go from this point to this point. And let's say at the slowest point of the year, it takes 30 days to go from here to here. See the difference?
Yeah.
Right. See if I can draw this. If you, using your friend calculus, determine the area swept out in each of these periods, the area of period 1 and the area of period 2 will equal each other.
So
yes.
We don't experience any difference in time or speed really because
we wouldn't feel any difference in the speed for a number of reasons, but the Earth is going slower at some parts of its orbit than others.
But does the time, affect the amount of daylight that we have?
No. Well, if it does, I mean, even though daylight has to do with the rotation of the Earth, there is going to be some effect because your angle around the sun is changing differently, but it's so small that it would be I mean, you'd really have to go out on a limb to detect it with special equipment. So the answer is no. For all intents and purposes, it doesn't affect the length of the day.
I guess another way of saying does it affect the speed of the orbit of the Earth? Of its...
Oh, no. It does not affect the rotational speed of the Earth.
Rotation, right.
Yeah. So the Earth rotates around its axis and revolves around the sun. Right? Yes. Okay. So this is one of Kepler's, Johannes Kepler's laws of planetary motion. They moved in ellipses. They followed these laws of speed and area. However, he had no idea of what underlying equation could have caused this. Well, that's where Newton came in and said, well, look it, if the force of gravity equals this, it results in this. So Newton found an underlying principle even deeper. The Kepler's laws were basically, they were a good observation, but Newton's law of gravity ties it all together. So I wanted to make this point about how Kepler and Newton are connected that way. And now what we're going to do is, we have to talk about one more thing with gravity. We'll pick it up in the next lecture.